AI gave us these fantastic tools to speed up a lot of processes, and I think these can be helpful almost at every step along the process. So we are right now using it at very early stage, so kind of at the design stage where we're conceiving a new CAR T-cell product, but I'm convinced that there's also people are already working on this and also already having successes with using AI also along all the other manufacturing steps, but also testing to help basically with experimental design and pipelines and how we then vet these cars. So yeah, I think all of those, and any stage, all of those, yeah.
Welcome to EHA Unplugged, the official podcast channel of the European Hematology Association, EHA. I am Leah De Leon, and today we are joined by Dr. Andrea Schmidts, Emmy Noether Group Leader and Principal Investigator in Medicine 3 Hematology Oncology at the Technical University of Munich in Germany, where she leads a translational research group on CAR T-cell therapies. Dr. Schmidts is here to discuss with us today how to use AI to design the CAR receptors for CAR T therapy. Thank you so much for being here with us today.
Thank you so much for having me.
How have researchers historically designed CARs?
Historically, researchers have tended to kind of borrow from what was already out there. So for a whole of CAR T-cell technology, the development previously of so-called monoclonal antibodies was really a foundational technology, because monoclonal antibodies allow us to really specifically and in a targeted fashion bind to our target of interest. And also the good thing kind of with having had monoclonal antibodies around earlier, before CAR T cells were developed, is that also there was already a lot of experience in using these antibodies, and even up to the clinical level. So we also even had like clinical grade antibodies. And it was mostly these that initially researchers relied on in order to then incorporate them into these chimeric antigen receptors and use them for these engineering approaches.
And what about specifically on the choices made around the single chain variable fragment, the SCFE?
So the single chain variable fragment is like if you want, the condensed part, the most important, if you will, part of the monoclonal antibody that really mediates its specificity, so where exactly it will bind, and while reducing the overall size, because like a full-length antibody would be a bit too big, too clumsy, too difficult to incorporate into this more complex CAR architecture, and that's why researchers typically have just narrowed it down to this SCFV and used that for CAR engineering.
Okay, and what kinds of data did you need to train or guide this new AI model?
So the AI models that we are working with have been developed and made available by researchers who have been actually working on this like for decades. So it's really now kind of reached a bit of a tipping point, if you will, that these AI-based tool for specifically designing protein binders, so basically a protein sequence that can target and bind whatever I program it to bind. So this has been very long in the making, and it actually builds on research that has been done over decades. And also very recently, the Nobel Prize for Chemistry was awarded for very prominent scientists in the field like David Baker, who have been in this field of so-called de novo protein design. So meaning that developing a protein from scratch, not borrowing from something that nature already made or something, but really designing it basically computationally from scratch. And so we really have been leveraging these tools that these labs developed and that they have made available for the whole research community. So we did not train these models ourselves, but we came to it from a very specific angle where we wanted to use these protein binder design tools for this specific application in CAR T-cell therapies.
Is this exciting?
Yeah, I think these are it's super exciting times for all of us with these new developments that we have, and just the pace at which these new tools are developed. And also I think it's just fantastic that they are so quickly shared and made available to the community with this open science aspect. It's fantastic.
And you mentioned that you have to feed the data into the AI model. Can you talk about what you actually have to feed into it?
So in our case, since it's us basically telling the model make me a protein that binds a specific target. So we basically need to name this target and then also provide it in a format that the model can work with. And in this case, these models are structure-based. So meaning that as an input, we're not giving the model just the amino acid sequence, so basically the individual letters that the protein is made up of, but we are giving it the structure, so meaning the 3D model that a specific protein is folding into. And that is actually our kind of input that we put into the model. So we're telling it, this is a protein that has the following 3D structure. Please, or make me, generate protein binders that will target this protein.
Okay, and which aspects of the CAR did your AI system actually design or optimize?
So our pipeline that we're currently working with really focuses on the binding domain, which is the part of the CAR that mediates what target it will bind to. So this is really the part that we have been focusing. But of course, there are other colleagues in the field that also use AI for different aspects of improving CAR design. There are colleagues that use it specifically for improving manufacturing procedure, for example. So I think for also so many other fields, like AI really can come in at almost every step of the workflow.
And can you describe the model in accessible terms?
So in our case, as I mentioned, the input into the model is the structure, this 3D folding of the target that we want to bind to. And then on the other side, what we're getting out through an intermediate step for the binding domain that it suggests, it first also will just suggest us a certain structure, but then ultimately we also need to translate that back into an amino acid sequence. And that's then really what is the output basically for us, and that we then really start working with.
Perfect. And how did you validate some of this AI designed CARs experimentally?
So when it comes to the experimental part, the testing pipeline is actually quite similar. The pipelines that we previously used for normal or like for the antibody-based CARs that we also have been working with. And importantly, also every time that we were testing these new AI-based binder CARs, we always side by side in each experiment also included a standard, so like a legacy CAR or a clinically approved one, to always have that as a comparator and reference point for us.
What was the biggest difference you saw?
In a lot of assays, they actually behaved quite similar, so that in a lot of these, especially early time point readouts that we looked at, they behaved quite similar. But what we are now fully exploring, and that's where I also see some of the biggest potential that these AI-based tools for protein binders have, is to specifically use them in the context when you're dealing with a cancer that has developed a resistance. So meaning that the target that you initially went after has changed under this selective pressure from the therapy that you have been applying. And then you're dealing with a so-called escape variant, or like with a modified version of this antigen. And I'm particularly interested in leveraging these AI-based tools to then specifically redesign binding domains so that they can then either rebind these escape variants or deliberately also broaden kind of the space that these binders can target to just prevent and try to also overcome these resistances that we do see in the clinic quite a lot and that are a major problem right now.
And what about functional readouts such as cytotoxicity or proliferation?
So that comes later, further down the line. So the first step, and that's really the step where we leverage these AI-based tool, is just to get these new binding domains, which, as I said previously, were typically borrowed from existing monoclonal antibodies. And then once we have these binders, we incorporate them into the Chimeric Antigen Receptor architecture, resulting in the whole CAR. And we then express those in human T cells. And so that's then where all of these also functional testing and readouts come in, like cytotoxicity assays and looking at cytokine secretion and other properties of that these CAR T cells now have with these AI generated binding domains.
And how do you think AI could outperform or at least augment the human intuition that was in CAR design?
The biggest advancement or advantage really is that we're able to scale up things like with AI. So it's just the volume and the number of car designs that we are able to test. And I think it's also for us with human intuition very hard to predict what is a good car, like if we design it from scratch. And since we don't well know these design rules yet, of course we can also not really feed them into a model and just tell it, take this as a blueprint and then try to always use this when generating a new car against this other target. So instead, I think the big advantage really comes from the scale up, so that we're really able to test hundreds and thousands of designs. And I think that just increases the chances that we'll also, among those thousands, there will be also one that works really great.
For someone new to AI using this, do you have any tips that you can share that you maybe learned when you first started using this?
Yeah, so absolutely. It's been quite a learning curve for us. So maybe just as a reference, so we got very interested, kind of started this line of research about 3 years ago. And we pretty quickly just relying on such de novo designed protein binders that other people had published, had some first proof of concept data that generally it works to take these de novo designed binders and incorporate them into a CAR, and it will result in a functioning CAR T cell. So that was for us the first very important step, which we learned already more than 2 years ago. But then the process of then starting and making our own binding domains has been just a very exciting journey for us, and we've had a very steep learning curve. And we learned also that it's really still a kind of a multi-layer approach. And on the design side, as I mentioned, you can scale up almost to unlimited levels. But probably one of the key learnings that what we found is that it really narrows down a bit. The bottleneck for developing these is rather the experimental testing. So you need to really find a good strategy for experimentally vetting then these many hundreds and thousands of candidates that you may have, and for your specific application, figuring out which is a good, easy screening test that I can do just to narrow down to the really well-functioning ones.
How do we move forward from AI-designed cars in the lab to first-in-human trials, both scientifically and from a regulatory standpoint?
This is something that we are very interesting and kind of are starting the process to transition these into translational settings. So for now, we are pretty much working along the blueprint that has been used for basically every time you have a new CAR T cell product. So also whether it's AI designed or not, AI designed, but also we're just starting the conversation with the regulatory agencies, and just to see how they advise us on if, in addition to the standard vetting process that is quite established for a new CAR T cell product, if they see any additional needs just specifically because of the fact that these were designed using AI tools.
How do you integrate AI-guided design with high-throughput functional screening?
These models, they provide thousands and thousands of candidate binders, but the real bottleneck for us right now is the experimental testing. So here we kind of need to find ways to also scale this up to the level that we're now able to generate these new binding domains. And that's also one of the focuses in my lab right now, that we're really looking at pooled high throughput testing assays that help us to just narrow down from hundreds and thousands of new binder candidates to the ones that really work.
And how do you see AI integrating into existing CAR discovery pipelines? Do you think AI becomes an early stage filter, a design co-pilot, or something more central?
I think all of those, because AI give us these fantastic tools to speed up a lot of processes. And I think these can be helpful almost at every step along the process. So we are right now using it at very early stage. So kind of at the design stage where we're conceiving a new CAR T cell product. But I'm convinced that there's also people are already working on this and also already having successes with using AI also along all the other manufacturing steps, but also testing to help basically with experimental design and pipelines and how we then vet these cars.
How transparent does an AI model need to be for regulators and clinicians to trust cars it proposes?
So since I'm not a regulatory, may I so well answer that, but I am a clinician. And so my approach, I think here would be quite pragmatic in the sense that I think even if we don't understand the very last detail of the design process, in our case, the binding sequence that we get from the model, we always very rigorously and strictly vet it with basically the same process that we would also apply to a conventional car. So therefore, I think this fulfills the standard. If it's gone through all of the testing pipeline, then I would trust it. And on the other hand, I mean, we could also argue that with the classic old way of generating a new binding domain against the protein of interest, which would have been to immunize a mouse. So basically you would have injected whatever you want to target into a mouse and then waited that in an immune response, that mouse then develops antibodies against your protein of interest. And so in a way, that also is a black box process, you could argue, because you also don't, I mean, of course, we have a scientific understanding of what happens in the mouse during that immune response, as part of which these new antibodies are generated. But it's not that we control or design those processes at all. So therefore, yeah, I think I would take a rather pragmatic approach and say, even if it's AI designed, but as long as it's been rigorously tested, yeah, I would trust it.
What should we realistically expect? Do you think AI will change all immunotherapies, how they're designed, and accelerate the improvement of clinical outcomes?
I think predictions are hard, but for sure, I think they will accelerate. So I think that is a very likely outcome, that using these tools just will speed up the process quite a bit. If it also increases our hit rate in the sense that for all the clinical products that we develop at the research stage, but then later fail in clinical practice, if kind of this gap there going from the preclinical stage then onto the clinical product, if that will improve, I think that we'll have to see and also learn quite a bit more. But what is for sure is that whole process will be faster and we will be able to speed that up, at least the preclinical part, quite a bit with these AI tools.
And if you want our audience to remember one thing from this podcast, what would you like it to be?
I think we are entering a very exciting new age, and we now have these fantastic tools at hand. And yeah, I'm just very excited for what the future holds, employing these AI tools now also specifically to cellular immunotherapies.
Well, thank you so much for joining us today. We really enjoyed this conversation.
Thanks a lot for having me.